Okay, so good afternoon, everybody, to this. I think it's the sixth lecture in CFD, and today we will continue with finite differences. So there's a little bit more I wanted to say about spatial discretization, but then we will mainly look at the temporal discretization, and then we will go to the next chapter, which then really brings us closer to CFD. We will start about the analysis of the discretized equations, and in particular how to show that what we do is actually stable and consistent with the governing equations. So that's kind of the plan for today, and also the first hour for tomorrow. I said it before, tomorrow the second hour will be devoted to the homework problem, homework number 1 and 2. So there will be just one lecture tomorrow, 1 hour of lecture tomorrow. Okay, but then let's start with a short summary of what we did yesterday, and I guess we can summarize it quite easily. So we were looking at finite difference schemes and how to derive them, how our notation is, and I guess the important aspect here is everything is in some way based on a Taylor expansion. A Taylor expansion of your solution, and then you just combine different Taylor expansions such that those error terms that you want to disappear actually disappear. So that's really the underlying idea of finite difference schemes. And with this in mind, you can construct schemes of different order. You can construct them on non-equidistant grids, whatever you like. It's always Taylor expansion. We have then looked also at two different ways of characterizing how accurate a finite difference scheme is. The first thing we looked at was the truncation error. The truncation error, as we will see later on, is in principle just the difference between the exact and the exact expression and the discretized expression. And whatever is this difference is, of course, the error, and that is the so-called truncation error due to the discretization. That's the idea. And by studying this truncation error, we can then find out what the order of a specific scheme is. So for instance, if the truncation error has a term that is proportional to delta x in it, then we call the scheme to be a first order scheme. If this truncation error, so the leading error term, is of second order, so delta x squared, then we will talk about a second order scheme. So that was one way to study the accuracy. The other way that we started to look at was based on the so-called modified wave number. And there the idea is that we don't do a local analysis in terms of the truncation error, but we actually do a global analysis based on the wave number of disturbances or of the solution. So what we want to do is, or what we want to calculate is the error as a function, or the error of a derivative as a function of the wave number. And therefore we have introduced this concept of a modified wave number, where the adjective modified comes from the fact that we assume that the finite difference schemes modifies the multiplication with the wave number in the spectral derivative. So what we then get is a modified wave number as a function of the real wave number. And we have calculated that for one example, a very simple example, but you will actually do a more complicated example in the homework. But for our simple example, which was just this central finite difference scheme of second order, what we got was a modified wave number that kind of looked like this. So the delta x times k tilde was the same as the sign of delta x times k. Maybe just one comment. I'm writing here delta x times k and delta x times k tilde. The reason why I'm doing that is to make this dimension less. Keep in mind the wave number is an inverse length. So in order to be non-dimensional, I need to multiply this by a length. And the only length scale here is delta x. So I typically consider delta x times k as the non-dimensional number. So if I then plot this, as I have done in this sketch, I can see that this one here, this line would correspond to the exact modified wave number. So if I had a perfect derivative, it would be like this. And the modified wave number that belongs to the finite difference scheme of second order, it looks like this. You know, it's essentially this sine wave or sine curve that I have there. And now the meaning of this plot or the interpretation is quite simple in a sense that you see that in this region where the two lines more or less coincide, and that means that the derivative is actually quite accurate. And this region corresponds to low wave numbers, so that means this corresponds to large scales. So derivatives of large scales compared to the grid spacing, they are represented very well with this central finite difference scheme. However, if you then look at this region here, where you have a large discrepancy between what the exact and the modified wave number is, you can kind of deduce from that there is quite some problem of getting an accurate derivative, and this is high wave number, so this would correspond to small scales. The difference here, or the modified wave number, goes in as a multiplicative factor in the derivative, as you kind of can. Well, you cannot see it here, but it's essentially, you know, the exact derivative would be something like this. So u prime numerical is I k tilde times e to the I kx. So you see that this is actually a multiplication here, and from this plot you can see that the modified wave number actually has a lower value, so that means that this multiplication is lower than it should be, which essentially corresponds to a damping of the derivatives at the small scales. And this, I guess, was the last thing that we wrote last time. In this region, or here we can say we have an accurate representation, whereas for the small scales we have increased damping of the derivative. So it means that the derivative at the highest wave number and wave numbers there are smaller than they should be, have a lower amplitude than they should be. And of course, this can create various problems. Okay. Well, there's maybe just one comment that I would like to make here. The example that I chose here was a very simple one. It was of a central scheme. Therefore, it turned out that the modified wave number was actually just a real number, in this case, a sine. If, on the other hand, if you have a non-symmetric scheme, so a one-sided finite difference scheme, so an asymmetric scheme, then the modified wave number in general is a complex number. So that means it's not just an error in amplitude, but it may also lead to errors in the phase of the derivative. So let me just write that down. Note that for asymmetric schemes, or asymmetric stencils of the finite difference scheme, the modified wave number is in general complex. And the fact that it's complex means that this leads to both amplitude and phase errors as a function of wave number. But this is something that you will look at in more detail in homework number 3, if I remember the numbering well. Okay, so this is what I wanted to tell you about the finite differences in space. Are there any questions to that? Okay, but then let's just continue with the next chapter, which is quite short, and that is about discretization in time. So before we have talked about space, now we talk about time. So far, discretization in space, and now we do time. It's actually not very different. It's kind of the same thing, just with the idea that, of course, in time, you have a specific direction in which you want to go. In space, it's maybe not so clear whether you go from left to right or from right to left. But in time, you always go from, you go towards the future, essentially. But let's just start with a very simple example. So if we take a differential equation and we take our linear wave equation, the advection equation, so something like that, then we have seen that so far we could approximate the space derivatives with finite differences in space. So what we did was that du dx at position I, we were approximating with, for instance, ui minus 1 divided by delta x. So this was, well, actually I can write it with an equal sign. So, and then we have an error, which was of the order of delta x. Okay, so what we can do now is we can actually insert this approximation into our differential equation. And that leads to what we call a semi-discretization. Semi-discretization just means that we just discretize space and leave time unchanged. Of course, in order to do that, we first just write it in kind of this way, that we say that the time derivative is a certain spatial operator, which in this case is minus du dx. And there's an a, of course, here as well. Well, actually, let me just take away the a. Doesn't matter. So a is 1, to make it simple. Okay, and now I can take my spatial discretization and essentially just put it in here, and that will then give me, this is equation 1, insert into equation number 1, and what I get is dy dt is a discretized version of this ln operator that I have just written here. So we just need to discretize this L operator, or this du dx, and that of course is exactly the then this finite difference scheme. Now there is one important point, or one important aspect that we should understand what we have done here. Now you see, I have written here, I still have written partial derivatives here for u, but actually it turns out that all the spatial derivatives, so the ddx, in the discretized form, have now been replaced by differences. So that means the only actual derivative of ui, so the grid function, is in time. So that means that these partial derivatives, they are actually just normal derivatives. So what we have done by this semi-discretization is we have done a transformation of a partial differential equation, so equation 0 in some sense, into a ordinary differential equation of the grid function. And of course, that is actually a very important step, because we have gotten rid of all the spatial derivatives, and we are just left with a time derivative, an ordinary differential equation in time. And of course, that means that the discretization in time essentially just means to integrate an ordinary differential equation in time. And that means we can use all the favorite schemes that you may have encountered earlier for integration of ordinary differential equations. So Runge-Kutta schemes, Adams-Bashforth schemes, etc. So that's what we need to do, integrate an ODE in time. So yeah, I guess that's it. So what we need to do is, well, integrate an ODE in time. That is now our purpose. Okay. So now let's get back to this this example that I had. Well, we wrote like this: du dt is the same as ui minus ui minus ui at time, let's say n plus 1 minus uin divided by delta t. So this would now be a typical first order approximation of this time derivative, exactly in the same way as we have done yesterday when approximating a spatial derivative. Just replace this t with an x, and then we had exactly the same derivative. And of course, this is not exact, so we have here an error that we commit, and in this case, the error is of order delta t. This is a first order scheme that I wrote down. Now, the important thing here is that I have two superscripts, and this would now correspond to the two different time levels. But of course, I'm using the same spatial position, so the I here as the subscript is the same for the three quantities. Okay, so this here is the time discretization of the ODE. And now if you put everything back together, so we go back to our semi-discretization, we can write that our ODE looks like this. We have dy dt is ln of ui. So this L operator that we introduced before. Yeah, and now actually comes an important point here, namely, if I combine everything, so I combine the time derivative and put that in here, and I take the space derivative that I have introduced up here and put it into the L operator that I introduced, there comes an important step or a distinction that I need to do. So let me just write it down. So I have ui n plus 1 minus uin divided by delta x, this is my time derivative, is ln of ui. Okay, but now the question is, I need to know at what time level I actually evaluate this ui. Should that be at the time level n, or should that be at time level n plus 1? Or, I mean, to maybe just write it down a little bit in a more straightforward way, if I just replace this ln operator directly with the finite differences that I have introduced here, this would be something like this: minus ui minus ui minus 1 divided by delta x. And the question is, what should I write up here as the index? Of course, the easiest way and the most straightforward way would be that I say, okay, I evaluate this at time level n, so the old time level. And that would correspond, if I just make a little sketch, if I have a time axis like this, I have a space axis like this, I have my 2 points. This would be This point here would be xi. This point would be xi minus 1. So that corresponds to ui and ui minus 1. And here I have tn, and this would be tn plus 1. Then the idea would be to calculate kind of the velocity at the new time. So this point here, I would use everything else from the old time. So essentially my stencil would look like this. So I would use xi minus 1 and xi to actually calculate the function value at the new time. So that's the most straightforward way of calculating or integrating in time. So I evaluate everything at the old time and then calculate my solution in one grid point at the new time. And this is also, I would say, the most straightforward numerical method for time integration, and that is typically called the Euler forward method, or what is also called the explicit Euler method. And that introduces one very important word, and that's exactly this explicit. Explicit means you calculate the value at the new time level based on all the values that you know at the old time level. So you evaluate in the semi-discretization, you evaluate the Ln operator at the old time level, the n time level. But of course, this is not the only way. The other way would be, and I just write it down in the same way, if you have uin plus 1 minus uin divided by delta t, you could also go there and say, okay, I evaluate the L operator, so the spatial derivatives, I evaluate those at n plus 1. I mean, formally, there's no difference in doing that. The accuracy of the scheme will still be of delta t, the formal order, but it would just look different in the sense that here it would be n plus 1 minus ui minus 1 n plus 1 divided by delta x. So the only change is that here I would use the new time level. And this scheme then, if I again try to draw a similar sketch as I did above, so like this, I have xi minus 1, I have xi, I have tn, I have tn plus 1. So now the idea is I would use this value, and this value at the new time level, so this and this, and at the old time level, I just have this value left. So this one here. So that means to calculate the new time level, essentially I would kind of, the arrows in some sense, they change because there is, or maybe I should do the arrows like this. So something like this. So from the old time level, the information spreads into 2 points. And of course, you can see that this is, of course, a big difference when it comes to the actual scheme, but formally, it's just that I take an n plus 1 here instead of an n. Now the method here is called an Euler method backwards, or also an implicit Euler method. Implicit, as I guess it will be clear in a second, implicit because you use the new time level for the spatial derivatives. Okay, now let's just look at these two methods a little bit in more detail. Let's start with the Euler forward, or the explicit Euler. So the explicit Euler method. Well, if you look at the equation that I get here, you can actually see that that we can simplify that and just write ui n plus 1 on one side and everything else on the other side of the equation. And what you get is actually a very simple rule of how to get uin plus 1. Namely, you just write uin minus delta t divided by delta x of uin minus ui minus 1n. So this is the rule of how I need to update my uin to get to uin plus 1. And it's based on uin and ui minus 1n. So exactly what I have written here in this, or drawn here in this little sketch. So that means I have exactly one equation, this one here, per grid point. One equation per grid point. And for me to implement that in a computer code, it's actually very simple. I just need to loop over each point and kind of calculate its new value at the new time level. So this is very straightforward, easy to implement. One single loop. But what will be the problem, and we will discuss that at length later on, it turns out that this method is not always stable, so it will not always work. In fact, it will turn out that there will be a problem with choosing this delta t. It only works if this delta t is sufficiently small. So I can only make small steps in time. And kind of, in some sense, is also clear to understand. In order to make this step, the difference in time needs to be small enough for this to be accurate. So what I can say here, but usually there's a limitation in delta t. And this is something that is actually quite common for explicit schemes. So schemes that use the information from the old time level to calculate one point at the new time level. This discretization that I just wrote here is at times also called a forward time backward space integration method. And this comes from the, it's kind of clear to what it means. It means forward in time. So that is exactly the explicit Euler. And then we have the BS comes from backward in space, because I use here backward finite differences in space. Backward in space. FTBS. We will use that a few times later on when we do some analysis of equations. Okay. So this was for the explicit Euler. So I would say the most straightforward way of doing a time integration. If we look a little bit in more detail to the implicit Euler, of course we can do in the same way. We can rewrite this equation. This equation here such that. We can rewrite this equation such that the everything at the new time level is on the left side, and everything at the old time level is on the right side. I can do that quickly. So what you get is 1 minus delta t times d minus times ui n plus 1 is the same as ui n. Now, what I did here, of course, it's like this. What I did here is I have actually used the derivative matrix I have used the derivative matrix that we have introduced earlier for this one-sided finite difference scheme that we used here to evaluate the spatial derivative. But if you do that, it's quite straightforward that you will see that this is the actual result. And now what you see, and that's kind of my point here, is that 1 minus delta t times this derivative matrix, this actually constitutes a matrix, which I can call A, for instance. So this would be, if you write it up as a matrix vector multiplication, this would be a matrix. Of course, what that means in the end for how to solve this system is that in order to get the solution at the new time level, so the solution at all the spatial indices at the new time level, I actually need to kind of invert this matrix A, so that I get ui n plus 1 is A inverse times ui. From a practical point of view, this means that I need to solve an equation system at each time step. So for each time step, I need to solve an equation system. And this equation system looks something like this: A ui n plus 1. So if this is a matrix, this would be a vector. And here it would be ui n. So I need to solve a system like that in order to be able to advance my time level from n to n plus 1. And of course, this is much more expensive and much more complicated to do than just following the rule that I wrote here for the explicit Euler. And also that is a typical consequence of implicit schemes, that at some point in the time integration, you need to invert the system. You need to solve a system. Now, how complicated that is, I mean, how expensive it is to solve that system, that of course is then a question that is dependent on the actual, the type of finite differences or the type of discretization you choose. Maybe also to some extent the accuracy that you want. You can think of iterative schemes, perhaps. Maybe this doesn't need to be solved very accurately. But still, the idea here is you need to solve a system which is more expensive or more complicated than just what you have done for the explicit scheme. So if I write that down, this of course is more difficult to implement, and typically more expensive to solve. Compared to the explicit time integration scheme. But, and that I guess if it was only disadvantages, we would not talk about it. There is of course a big advantage, and this advantage is that the stability limitations that you get from the explicit schemes are much less for implicit treatments. So there may be situations when the time step limitations for explicit schemes are so severe that you would actually like to go to implicit treatments where you don't have that problem. No time step limitations would be a step limitation. Is the big advantage here. Okay, so I guess this is what I wanted to tell you about time integration. The important take-home message is that time integration in the context of partial differential equations typically means that you need to integrate an ordinary differential equation after you have performed the semi-discretization, and then you can use all the methods that you like for the integration of ordinary differential equations. Just to make some, well, kind of name dropping, so other methods to integrate ordinary differential equations, and I'm sure you have heard, of course, of those, the Runge-Kutta schemes. That is something that is very popular in CFD or in general. This is actually something that we're going to look at in homework number 3, I think, or homework, no, I think homework number 2 even. So homework number 2. What you do there is you actually get higher order by introducing what is called substeps in the integration. But you will see that in the homework how this is being done. Then another scheme that we also will look at in the homework will be the Crank-Nicholson scheme. The Crank-Nicholson scheme is in some sense a similar to central finite differences. So it's a scheme that is in principle implicit because it takes the solution at the new time level, but also the solution at the old time level at the same time. So in that sense, it's central in space. And this method is quite a powerful method because it gives you an order of delta t squared. And so it's a second order scheme as opposed to the first order schemes that we have discussed now. And then also schemes that we will look at a bit later on. That is the Adams-Bashforth scheme, or the Adams-Moulton scheme. These are so-called multi-step schemes. The idea with multi-step schemes is that they don't only, so that the u at n+1 is actually a function of u at n, but also u at n-1 and u at n-2 and so on. So that's what a multi-step scheme is all about. Also, Adams-Bashforth schemes we will look at later in the course. I think it's homework number 5 when we have a small example. Okay, I guess that's what I wanted to tell you about time integration, and with this I would also conclude the chapter on finite differences. So, are there any questions related to that? Okay, but in that case, I would directly continue to the next topic or next chapter, and that would be part C of this introduction, and that is the analysis of the discretized equation. So let us now assume that we're at the stage that we have, we have defined our equation that we wanted to look at. So we have our let's say physical model. So that means we have in some way we have found out what the partial differential equation is that we want to solve. So for instance, an advection equation. We have looked at the type of the equation, so we have done the classification. So we kind of know what is expected. We know where to put the boundary conditions, what is needed to make it well posed. So we kind of know what we want to do. Then we have chosen the discretization. So according to what we just discussed, we have used finite differences, right-sided finite differences, or central finite differences, and an Euler scheme in time, for instance. So we have done this discretization. So we come up with a finite difference scheme and essentially an algebraic equation, or a system of equations, depending on what we have done. So we're at the stage now where we could actually put that into a computer and calculate solutions. But now the question is, how does the solution actually look like of this algebraic system? I mean, does this solution make sense? Does it corresponds to the exact solution of the partial differential equation? And do I have any freedom in choosing, for instance, the time step or the delta t or delta x? Or am I completely free in choosing these values? So I guess the question here is really, what we want to do is we want to analyze this discretized equation. So you want to see whether we can understand something just from the mathematics of it, how to choose the right parameters, how to know whether or not I get a correct or not result. Okay, in order to do that, we actually need to introduce a few concepts, and we will do that during the next 2 hours, let's say. And the following concepts are important for this. First of all, and that's then the next chapter that we will look at in more detail, we need to look at the concept of convergence. Convergence, I guess, this is our ultimate goal. We would like to converge to the correct result. So the idea with convergence is that our numerical solution should actually in some way converge towards the exact solution of the original partial differential equation. So if we go back here, we would like that the solution to this algebraic equation converges to the exact solution of the partial differential equation. Then the whole process of doing the discretization was actually successful because we get a solution of the partial differential equation that we actually wanted to solve. This is convergence. Now, the problem is, in order to show convergence, we would need, or in principle, what we need to do is we needed to look at the error of the exact solution of the PDE and the numerical solution of the PDE. So we need to do a difference of those and kind of get some error bounds on that. But the problem here is that we don't have the exact solution of the PDE, because if we had, why would you do a numerical simulation of it? So that means, in general, it's very difficult to show that we have actually converged, or you cannot even do it at all. So therefore, it has become, or the way to do that is actually to not show convergence directly, but rather to make a slight detour and show 2 other concepts, which we'll also discuss now, which then imply convergence in the end. So the steps we do is we actually look first at something that is called consistency, and then as the third thing we look at something that is called stability. Now, consistency and stability together, they are connected with a theorem which then will imply that convergence is given. We will write that down in a second. But let me just, before the break, write down the definition of consistency and stability. So consistency means that the discretized equation is actually the same as my partial differential equation. So the important aspect here is I'm not talking about the solution to it. I'm just saying that the discretized equation in some way converges towards the partial differential equation. Okay, this is not the solution, just the equation that is the same. Stability, on the other hand, means that the numerical solution that I get is converging towards the exact solution. But now I'm not saying the exact solution of the partial differential equation, but the exact solution of the of the discretized equations. And of course, these I have. That's the good thing. And now the idea is that if I can show consistency and stability, then I know that my scheme is actually convergent. And the step to go from consistency and stability to convergence is called the LR equivalence theorem, which I will talk very briefly about in the beginning of the next hour. So with this, I would like to take a break of 15 minutes, and after the break, we will continue briefly with these concepts, and then in particular the LR or the equivalence theorem, and then we will go into the details of consistency, stability, and convergence. Okay, but then I will pause the recording. Okay, so welcome back to the second hour. So what we talked about before the break was the three concepts of convergence, consistency, and stability. And as I was saying, it is typically very difficult to show convergence directly. Therefore, we go the detour via showing consistency and stability independently. And then there is this LR equivalence theorem that connects the two and shows that convergence is actually a result of that. And I would just like to write that down. So this LR equivalence theorem states the following. Actually, maybe just to say, LR stands for Lax and Richtmeier. These are two scientists or mathematicians that have proved this theorem for the first time. Sometimes this LR equivalence theorem is also called the Lax theorem, but it's kind of the same thing that is meant with it. So what does it state? Given a linear, well-posed initial value problem, if the finite difference approximation, approximation is consistent and stable, convergence is implied. And that is actually, and that's a good thing, this is a necessary and sufficient condition in this whole process. So just to write it down, so if we have consistency and we have stability, then we get convergence. Okay, so there is of course a little problem here, namely this is technically only valid for linear problems, and it's for initial value problems. So there is actually the question of boundary conditions is not discussed here, but in these cases still it is if you have consistency and stability, then you have a necessary and sufficient condition for convergence. There is other ways of showing stability and all of that for also more complex situations, but for the purpose of this introduction, the LR equivalence theorem is typically sufficient. So what it means now for us is we need to explore what consistency and what stability means, and of course we perhaps want to start with the concept of convergence, because that's in the end what we would like to achieve. Let me now go through these three topics one by one to just kind of know what we're really talking about. We start with the concept of convergence, so the actual goal that we have. So first, we look at convergence. As I said, this is what we really want to have. So the main question, or the main kind of the summary of convergence is, does the numerical solution that I obtain approach the exact solution of the PDE? That is the idea of convergence. Do I converge to the right solution? And also here I can write that a little bit more formal. So convergence, the definition of convergence is that some norm of the difference between my numerical solution and the exact solution, which I write in this way. So ujn minus u at xj and tn. So this norm should be smaller than some constant times delta x to the power of p plus delta t to the power of q. Now delta x here corresponds to the grid spacing, and delta t corresponds to the time step. And this convergence should of course be should hold if delta t and delta x go to 0. And the constants c, p, and q are numbers larger than 0. P and q, they are actually called the rate of convergence. So I mean, you can have, you know, first order, second order, and so on. So this essentially is what we want to achieve. We want to achieve that our numerical solution, or the difference between the numerical solution and the exact solution, goes to 0 if the grid is refined. And as I said, this is very difficult to show. If or because u at xj and tn is actually unknown. And of course, that's the whole point of the numerical simulation. Okay, so this is convergence. As I said, we cannot do that. That's why we go the detour via consistency and stability. So let's now directly continue with consistency. This is something that we can actually show, and we also need to show for numerical schemes. The basic idea of consistency is the question of how well do we approximate the partial differential equation? How well do we approximate the partial differential equation with our numerical scheme? That's the question of consistency. So also this we can define in a little bit the formal way. I'll just write that down quickly so that we also have kind of the mathematical language behind it, but we don't need to spend too much time on that. So if we do that formally, so we have the partial differential equation, which we can formulate as kind of an operator p, which is a function of x and t and the derivatives dx and dt maybe. And this partial differential equation, of course, can be applied to a function u, and we have some right-hand side, and we have some initial conditions, for instance, x0 equals g. So this is kind of a formal way of writing our partial differential equation. We can do the same thing on the discrete level, and there we just do our usual formulation by adding an n to make it discrete. And of course, then it's again depending on x and t, but instead of the derivatives, we have delta x and delta t. And this we can apply on a numerical solution. And this is the same as a discrete right-hand side, and we have a discrete initial condition. Like this. So this defines us an operator P and an operator Pn. And now, based on that, we can now try to answer our question how well Pn approximates P. And this we do with the help of a local truncation error. I guess you remember the word truncation error that I mentioned before for finite difference schemes. That's exactly the same concept. The idea is what is the difference of my discrete operator compared to the continuous operator. So the difference between P and Pn. And that's exactly what truncation error is about. I call it T, and it's local because it's a function of xj and Tn. And that is essentially P applied to some function minus Pn at Vn, evaluated, of course, at this position, xj and Tn. So this is my truncation error. It's just P minus Pn, essentially. Okay, and now if I go one step further, what is now consistency? Well, it just means that this difference between the two operators goes to 0. So consistency now means that the norm of T at xj and Tn is smaller than some constant times delta x to the power of P plus delta T to the power of Q. And again, this is valid for C, P, and Q larger than 0. It actually turns out, if you do that formally, you can have here even a time dependence on this constant. But this is not relevant for us today, so we will not mention that further. P and Q, they are called the consistency order of the scheme. And I mean of the scheme of both the temporal and the spatial discretization. And if we talk about the order of a scheme, then it's typically the consistency order that we talk about. So if I say, I have a code OpenFOAM is second order in space and first order in time, then actually I'm talking about this P and Q. It's the consistency order that I mean with that. Okay, so this is consistency, and actually to show consistency is not very difficult to do. And I will just do that on one simple example so that we can kind of understand what is meant by that. I take the advection equation. You will see many of my examples are done with the advection equation. And of course, the reason for that is really that this is the simplest partial differential equation that has some relation to the convection or the transport properties that we look at in fluid mechanics. So it's the advection equation. So du dt plus a times du dx is 0. And I'm discretizing that with forward time, backward space, as I was mentioning before. So this is just the forward time, so an explicit Euler for the first term, and then it's a backward finite difference for the second term. So the fully discretized system would then look like this. I have ujn plus 1 minus ujn divided by delta t plus a times ujn minus uj minus n uj minus 1n divided by delta x is 0. And now what we would like to show is the consistency between these the consistency between these two equations. So consistent. So the consistency between the partial differential equation and the discretization. Yeah, so how do we do that? And well, the way to do that is kind of, you know, a little bit backwards in some sense. It's just using Taylor expansions, but now we do it in the other way around. We're not putting it into the PDE to get a difference equation. We actually do the Taylor, we put the Taylor expansion back into the discretized equation, and we see whether we can recover the partial differential equation. So the idea, we do Taylor expansion. Okay, so how do we do that? Well, essentially, we need to replace all the different terms here with adequate Taylor expansions. And in this particular case, we see that we have un plus 1 and un. So we need to do a Taylor expansion in time. And we have uj and uj minus 1. So we need to do a Taylor expansion also in space. Yeah, so let's do that in time, perhaps. So we have ujn plus 1, and that will be ujn plus delta t times ut. So ut here is shorthand for the first derivative in time, plus 1/2 delta t squared of utt. Utt is the second derivative in space, in time. And then we of course have some terms which are of third order in delta t. There's a question that somebody asked in the chat whether the truncation error is always a local error. Well, I mean, it's local in that sense that that you can evaluate it at a specific position. So yes, in that sense, it's local. So what I mean with local is that it's measured as a function of x and t, as opposed to, let's say, an error in spectral space where I would look at it as a function of wave number. So in that sense, it's local, yes. So this t here, actually you directly see it from here. This t here is a function of x and t. So that's what I mean. Okay, so if you go back to my my Taylor expansions, so I have the expansion in time. So that means I can use this to express this term. But I also have one guy in space, and that is this one, uj minus 1n. And also this one I need to expand I need to expand with the Taylor expansion. So that will be ujn. Now, because it goes backwards, I have a minus here. That is delta x times ux. Then I have 1/2 delta x squared uxx. And then I have some stuff that is of higher order. Okay. Now, if I call this one to be equation 1, then I just need to insert that into equation 1. And then we will see what actually remains. So I put these Taylor expansions into equation number 1. And what I get, I'm now doing everything at once, so to save a little bit in writing. But if you just look at it, what happens if I put ujn plus 1, or the Taylor expansion of ujn plus 1 here, you can see that I get ujn minus ujn, meaning that the first term will disappear, and then what remains is the second term and the third term. And of course, the same thing happens here for the convective term as well. So what I will get as a result is du dt plus a times du dx, but then I will get some terms on the right side, which are essentially these guys here. So minus 1/2 delta t utt plus a times 1/2 of delta x uxx plus order delta t and delta x to the power of 3. So this here is what I get when I put everything into the fully discretized equations. Okay, and now we would like to calculate the truncation error. So that means I need to calculate the difference between the exact equation and the discretized equation. So with this, I can now say that t, as a function of xj and tn, will be, well, so I take the exact minus the continuous, the exact minus the discrete equation, which is then my truncation error. So what you see is that this part, of course, disappears. So what remains is essentially this on the right side. So I get minus 1/2 delta t times uxx plus 1/2 a times delta x times uxx plus order delta t to the power of 3 and to the power of 2 and delta x to the power of 2. Here it should of course be a power of 2 as well, because I have already divided by 1 delta x with 1 delta t. Okay, so this here is now my truncation error. And now we need to see whether my scheme is actually consistent. And the idea of consistency we have written here. The idea of consistency is whether we can define exponents p and q with which the difference between the continuous and the discrete equation goes down. And of course, if we look at that, we can see that in this case, we have an exponent of q being 1, and here we also have an exponent of p being 1. So this means that q is 1 and p is 1. And the conclusion of this means that the truncation error is of order 1 in both space and time. And this essentially means for this scheme that the scheme, so the forward time backward space scheme, is indeed consistent. Consistent again means if you grid refine, it will converge to the original partial differential equation. And keep in mind, I did not say anything about the solution. I did not compute the solution here. I just looked at the actual scheme. So I don't know whether I get a good solution or not. I just looked at the actual numerical scheme, how I wrote it down. That was the only thing that I looked at. Okay, so this is consistency. There's one last step that I would like to just briefly mention, because you can go one step further from this, because you see, actually here I made a mistake. I see now this of course should be utt. So you can go one step further. Namely, you can see that I have utt and I have uxx here. And it actually turns out that these two terms are related to each other. So what we can do now is we can use the partial differential equation to relate uxx and utt with each other. Well, how do we do that? Well, we just derived the partial differential equation both with respect to x and with respect to y, and then exploit that uxt is the same as utx. And what we get for that is utt is the same as a squared times uxx. So I'm just using the theorem of Schwarz, or the equality of the mixed partials. So this is the result. And if I use an abbreviation, sigma being a times delta t divided by delta x, just as for the time being as an abbreviation, I can then simplify my truncation error as, or simplify, rewrite it as t is the same as 1/2 a times delta x times 1 minus sigma times uxx. So in this way, I just have one term that gives me the truncation. And of course, this term is still first order in space, so I still have a delta x here. But it's still consistent in the sense that if delta x goes to 0, then it will remain. I mean, the error will go to 0. We will later in the course see why this form actually might be quite important for us to understand how specific solutions of the advection equation will look like. For the time being, it's just kind of a mathematical, an analytical way of rewriting the truncation error. Okay, so this is about consistency. The question of how well do we approximate the partial differential equation. And of course, it makes sense that we need to be consistent if we want to have a convergent scheme. Because imagine if you have a numerical scheme that is not consistent, that would simply mean that if I grid refine, I would not approximate the right equation. And then, of course, it's obvious that this would not converge. Or, obvious and obvious, it may actually be, or there are schemes that people have developed that were not consistent. And it took, some time until they actually discovered that these schemes are not consistent. I just put it here as an example, which you may want to look at if you have some time. There is a scheme that is called the Dufour-Frankel scheme. I think it's 2L. The Dufour-Frankel scheme. No, it looks like 1L. I'm actually not sure. The Dufour-Frankel scheme, which had some issues for certain parameters with consistency, or rather, consistency is only given if delta t and delta x vary vary together. Okay, so this was consistency. Do you have any questions about consistency or truncation errors? Okay, then let's go on and now go to probably the most relevant concept, and that is the concept of stability. And of course, this is something you have always, you all have heard of. When doing simulations or CFD, your code blows up or your simulation blows up. That is what we mean with stability. So let's say a simulation blows up. That's what we mean with stability, or actually that's an instability if it blows up. So what we need to do is we need to understand when or what conditions need to be fulfilled that a simulation does not blow up. But if we kind of start from a more formal level, what we mean with stability. So I guess the idea is that a stable numerical scheme means that errors do not amplify. Do not amplify in the way that they start to dominate my solution. And of course, what I mean with errors, these could be errors from truncation. So truncation, again, that's the idea of having a discrete mesh versus a continuous one. So these errors, but also errors from round off, so that I do an inexact calculation, so that I don't represent a number with its full accuracy. So it's that these errors do not amplify. Yeah, I mean, errors do not amplify. That's essentially what stability means. Now, what does it mean now for us, or how can we kind of understand how to measure stability? Well, again, let's do that a little bit formal. So consider a scheme P Pn of un equals 0. So that's just a way of writing a scheme. Now, we would like to reformulate that as a time stepper. So in a sense that we want to go from one time step to the next time step. So we can rewrite that in explicit form. So we can say that un at n plus 1 is just some factor which I can call g, which is a function of delta x and delta t, and of course a function of p. But this amplification can then be applied to un. So imagine I have un, and I just want to go from un to un plus 1, and imagine that I just multiply that with a factor g, an amplification factor g. And so this is an explicit form of my numerical scheme. And of course, if I do that, I also need to somehow give the initial condition. So the initial condition would be u0, un0. So un0. This is the solution at time 0. And of course, that means now that I can formulate my time integration as kind of a sequence of multiplying the initial conditions in the initial condition with g. So starting from the initial condition, so time 0, at time 0, well, if I have here my un0, I multiply that with g, then I get that this is then un plus u1n. I multiply that again with g, that gives me then un2, and so on. So I have multiple g's here. So in the end, I can then very quickly see that this is g of un n minus 1. And of course, this is then un at n. So it's just a sequence of applying g to that. And of course, if I count how many g's that is, it's g to the power of little n applied to un0, my initial condition. So that's the way that my time integration would work. I just amplified each time step. I amplify my solution with another version of g. Okay, so this is very good. But now, if we assume that we have errors in the solution, so consider a linear error. So we say that we have, we're not solving for un, but actually we solve for un time plus an error epsilon. And I can also call it it's a discrete error because it's an error that lives at every grid point. And so I just say that this is epsilon n. And of course, now the question is, okay, how do I time integrate this new equation, which is un plus epsilon n? Now it turns out, because this is linear, this just means that this equation the error fulfills. So consider a linear error of this form, and this fulfills the same discretized equation. So that means essentially that Pn of epsilon n is also equaling 0. So it's not just my numerical solution, but also the linear error that I add to it solves the same, or is a solution to the same propagation of through the timestamps. And of course, by virtue of this equation here, which gives me un at time n, I get the same result for epsilon n at time n, which is just g to the power of n times epsilon n 0. So the error, an additive error that I had in the initial condition would just propagate through the whole thing in exactly the same way. Yeah, what does that mean? Well, it means that the error is amplified with the same operator, G, as the solution is amplified. Now I guess you have kind of understood why I use G and why I always use the word amplified. G in the end is what is called the amplification factor, or the amplification matrix, if you think of a matrix problem for the specific discretization. So this G is a very important factor for a numerical scheme, because it really tells you how I go from one time level to the next time level. And in a matrix formulation, I can represent explicit and implicit schemes in exactly the same way. Now, if you go back to our definition of error, of stability, where we said, well, stability for us means that errors do not amplify. Yeah, that now means for us as the if we have an amplification factor for a specific numerical scheme, well, for us it means that stability means that some norm of this G needs to be lower equal 1 for errors not to amplify. So that's essentially the idea of stability. So we need to, in some way, find out what this G operator is. So how we go from one time step to the next, and then we need to see what the norm of that is and make sure that it's below 1, so that we don't have amplification. That's essentially what we would like to do. And of course, now we need to do a few examples to understand that better, to see how we can actually calculate that. Now, the first example is to study the stability of an ODE, of an ordinary differential equation, with exactly this method. Why do we consider an ODE to look at stability? Well, the reason for that is, if we just go back to the beginning of what we talked about today, somewhere here, well, we have actually seen that even if we do partial differential equations, at some point, we are integrating an ordinary differential equation in the context of a semi-discretization. That's what we do at some point. So therefore, it is very relevant to understand how to time integrate an ordinary differential equation, or how to integrate an ordinary differential equation. So we start, or we look at, I would say, the simplest possible ordinary differential equation, that is u prime equaling lambda times u. And people call this also the Dahlquist equation. Dahlquist was a mathematician or numerical analyst in Sweden, from Uppsala and later on also at KTH, who was one of the first that started to study the stability properties of ordinary differential equations, and coming up with a lot of the basic proofs in this area. And he was active here in the, I guess, in the 50s, 60s, and therefore there's many important works that go actually back to him. And I guess in his honor, this equation has typically gotten the name Dahlquist equation. The lambda, the coefficient here, can be actually a complex number, so it can be lambda r plus lambda I. And of course, u prime and u. So u prime is the derivative, and u is the solution. Good. So how do we solve this? So first of all, maybe it's interesting to look at the exact solution. So the analytical solution of the Dahlquist equation. And of course, I guess it's quite straightforward to see it's the derivative that is the same as the function with a coefficient. So I guess it's clear that u of t is some exponential e to the lambda t. And then of course we need to have an integration constant a, which we can then determine with the initial condition. So a comes from the initial condition. So this is our exact solution. Now, we can also just formally define what we mean by stability for our exact solution. So the stability for the exact solution. So in the same way, kind of saying that u should not grow over time. And then I guess it's quite clear what conditions need to be fulfilled such that that u is not growing. Namely, the condition is that the real part of lambda needs to be lower equals 0. Otherwise, of course, you will have exponential growth. And that's just a consequence of the lambda being here in the exponent. So the condition for stability of the exact solution is that lambda r needs to be lower equal 0. So let me write it like this. Lambda r being the real part of lambda should be lower equal 0. If I draw that in a diagram where I plot lambda I, lambda r, so this region here would be the region of stability for the exact solution, or the analytical solution. And now I guess the question is, if we now start to discretize this equation, do we get the same region of stability, or do we get something else? And I guess now it's 5 o'clock, and I guess we'll continue to talk about that tomorrow at 10 to see whether we can actually get some stability limits for time integrating that with a discretized version. Okay, but with this then, I guess I will stop for today, and